We're going to take a look at this problem. Block B is initially at rest, and block A slides down the smooth ramp and collides with block B. Block A and B couple together after impact, and the velocity after impact is 20 feet per second. What was the initial velocity of block A when it left point P? So let's take a look at this. So we're going to have to work backwards in something like this, since we're given the final velocity. So we're going to have to use conservation momentum, and we'll take the mass of A times the velocity of A before impact. Maybe, I don't know if you want to call that V1, or VA1, and then mass of B times the velocity of B before impact. Then they collide and stay together. And then we'll have like some final velocity where they're both together. Now we're told what that final velocity is. And so again, this is just before impact, this over here, just before impact, and this is just after impact. Now we know the mass of A was 10 pounds divided by 32.2 or maybe 32.17 for gravity. Times the velocity of A1, let's call it. Then B has 18 pounds divided by 32.17. Now, the velocity of B, it was at rest just before impact. Then we're going to have the mass of A plus the mass of B just after impact. And then we'll have our final velocity like this. So if we put all this into the calculator, and oh, by the way, we do know this final velocity. We're given that that's 20. Feet per second. So now if we solve this for VA, we get that the velocity of A was 56 feet per second just before impact. But now we want to know the velocity when it was way back here at the top. So let's take a look at this. Okay, we know down here, we just found out that A had a velocity of 56 feet per second. And we want to know what happened up here. And that's 24 feet above the ground. And now we can use, like, say, work energy or conservation of energy, whichever you prefer. Let's try maybe conservation of energy. So that would be, so let's say at the top. So at the top, now we're going to need some kind of a datum line. Maybe we'll call at the bottom here the datum. And so let's say when it was back at the top here, so we would have had, let me call T for the top is 1/2. This is the kinetic energy. And so this would be 1/2. Remember, this one is 10 pounds. 10 divided by 32.17 times the velocity of the top squared. And the potential energy when it was at the top is going to be the weight times the y. And this would be the distance above the datum line. And so it weighs 10 pounds. And it's going to be 24 feet. And so this is 240 pound-feet. Then at the bottom, we have TB. Again, 1/2 mv squared to 1/2 10 divided by 32.17. Now the velocity at the bottom we know was 56. And if we put this into our calculator, we get 56 squared. And this comes out to be 487.4, and that's going to be pound-feet. Now the kinetic energy at the bottom due to the weight, again, it's going to be the weight, 10 pounds, times the distance above or below the datum line, but it's right on the datum line, so that's going to be 0. So let's put everything into our equation. T1 V1 is equal to T2 V2. Again, T1 is going to be at the top here, the initial point, and that's going to be this here. This is, I'm going to divide the 2 into the 10, so I'll give us 5 divided by 32.17 velocity top squared plus 240 equals 487.4 plus 0. And let's calculate this. Minus 240 times 32.17. And so it looks like the velocity squared is 5091.8. If we take the square root, we get 39.9. You could maybe round off to 40. So the velocity at the top is going to be 40 feet per second. So in this case, this problem, we had to use conservation of momentum to find the velocity just before impact of A. Then to find the velocity at the top, we had used conservation of energy. You could also have used work energy and would have gotten the same answer. Next, we're going to take a look at this problem. The 15 kilogram block A slides on the surface for which the coefficient of friction is 0.3. The block has velocity 10 meters per second when it is 4 meters from the 10 kilogram block B. If the unstretched spring has a stiffness of 1,000 newtons per meter, determine the maximum compression of the spring due to collision. take the coefficient restitution E to be equal to 0.6. Let's take a look at this problem. So this is going to have to be analyzed in 3 different steps, it seems. So we're told at the beginning here that this was going to be 4 meters from here to here. And so there's gonna be 3 steps. So step 1, A is from the current position. So let's consider like this would be step 1. This would be A, say A from the current position until A reaches B. So it's going to be like starting here, and then just when it reaches B will be the step 1, and then step 2 will be the moment A impacts B. And step 3 just after A impacts B and B compresses the spring. So let's look at those 3 cases then, or 3 steps, I should say. So again, let's take a look at step 1. So A comes along here. And it just gets up to B. And now during that time, of course, let's see, we're told that A is 15 kilograms. So that means it's going to be 15 times 9.81 pushing down. And that's going to be the same pushing up. 15.981 times 9.81. Excuse me, that's 147.15. And then while it's going from the original position to B, it's going to have friction that's going to be resisting that. And of course, the friction is always going to be mu times this normal reaction, which we said that was 0.3 times 147.15, which is 44.145 newtons. That's going to be the friction force when it travels from here just till it gets to the point that reaches B. And so we can do this with work energy. Again, T1 summation U 1 to 2 is T2. And remember, this is energy 1/2 the mass, which was 15 kilograms for A. 1/2, and then the velocity squared. And we're told that the initial velocity was 10 meters per second. And then the work done from going from the initial spot till it reaches B is, again, the work is going to go against the motion. So that's going to be our friction times the 4 meters that it moved. So again, this is going to be the friction times the distance, if you want to call it maybe S. And then this is going to be equal to 1/2, again, the mass times the velocity squared. Again, that's going to be the velocity just before impact. Oh, by the way, I forgot the square here. The kinetic energy is 1/2 mv squared, so there should be a square right here. And so if we put 75 minus 44, 145 times 4 times 2 divided by the velocity squared comes out to be 76.45. And we take the square root, we get the velocity just before impact of 8.74 meters per second. That's a velocity of A just before impact. So step 2, this would be, say, the moment A impacts B. So again, now they've actually made contact and impact. And the mass of B was 10 kilograms. Mass of A, we said, was 15 kilograms. So here A impacts B. And we're going to need a couple of equations. Again, conservation momentum, mass of A, velocity of A before impact. I don't know how you want to describe that. Let me just leave it that way. Let me say, what did I call it before? I called V2. Okay, let me call it V2. And then the mass of B, VB2. And then the mass just afterwards, after impact. The velocity just after impact going to be MA, VA. Maybe let's call it 3 just after impact. MB, VB3. So again, this is just before impact, just after. So before on the left and after on the right. We put some things in. Of course, the velocity of B before impact was 0. And again, A was 15 pounds, 15 kilograms. And the velocity of A was 8.74 plus 0. Then just after, it was 15 kilograms VA3 plus the mass of B, 10 kilograms VB3. So now, if we multiply these two together here, 8.74 times 15, we get something like 131.2 over here. Let's solve maybe for VA, velocity of A3. There are probably several ways you can do this, but let me solve for this. So there's still 10 over here. And so, yeah, let me do 15. This is 131. Let me call it 1/6. And if I keep that, let me bring that over. So it's minus 10 VB3, like this. And if we divide through by 15, we get VA3 is equal to 8.744 minus 0.67 VB3. So we have one equation, but two unknowns. So we're going to use another equation. So let's call this equation 1. But now we also have the coefficient restitution. So this is E equal to VB. Now we're going to have to use the numbers we're using here, maybe 3 VA3 divided by VA2 minus VB2. Now, of course, the velocity just before impact. So again, the 2's mean just before impact, 3's just after. And of course, this one's going to be 0. And so if we plug in all the numbers here, the coefficient restitution was 0.6. And we're going to get VB3 minus VA3 divided by VA2, which that was just before impact. And we know that that was 8.74. And now we can solve these. We can multiply this over here. And we can get that V, in fact, if we solve for VA3, well, let me do this in steps here. If we multiply this over, this is 8.74 times 0.6, 5.244 equals VB3 minus VA3. And if we solve for, let's say, VA3, that's going to be VB3 minus 5.244. Call this equation 2. Again, there are several ways you could solve this because we mainly just ended up with 2 equations of 2 unknowns. What I decided to do is solve for this. And this is VA3 and this is VA3. So we can set these two equal to each other. And so that's going to give us 0.744, 0.67 VB3, VB3 minus 5.244. And then if we solve for VB3, we get that VB3 is equal to 8.377 meters per second. Then if we put this into any of the other equations, we can find, again, we can put it either into equation 1 or equation 2 to get VA3. Let me put into equation 1. VA3 is equal 8744, 67, 8.377. And this comes out to be I'm getting 3.132 meters per second. That's the velocity of V. So here we have the velocity of B just after impact. And down here's the velocity of A just after impact. Now we're mostly interested in the velocity of B because that's what's going to be going against the spring. So step 3, we're going to have to look at the spring compression. So now B is going in this direction now at 8.377 meters per second. And actually, A is also going in that direction, but it's going at a slower rate because, again, they've collided and separated. And so now, this time, again, there's going to be friction under B. Again, remember, B was 10 kilograms. So it's going to have a normal is going to be 98.1 newtons. And again, there's friction over here. Again, the friction force is going to be, as always, mu times the normal, which is going to be 0.3 times the 98.1. And so I'm getting about 29.43 newtons would be the friction force. And then also there's going to be the spring compression. So the spring force, well, actually, we don't need to calculate that right now. So we want to do, say, work energy. So let's use work energy. So now the work is so there's going to be a couple of things for work. One is going to be the spring work. That's 1/2 K S squared, depending on how far the spring is being compressed. In this case, this is 1, and the spring is 1,000 newtons per meter. Times S squared. And then there's also going to be friction work. Again, that's going to be the friction also times S, whatever distance we have. And this is 29.43 times some distance S. Now notice that these are both opposing the motion. The spring is opposing the motion, and so is friction. So we have to put a negative here and negative here. Again, opposes. So that's why we have the negatives here. And so finally, again, the kinetic energy. So before, say that just after, let me call this, let me just call it T1, but this will be just after, let's say, yeah, just after impact. So after impact, you have 1/2 M V1 squared. That's 1/2 10 kilograms. And the velocity just after impact, we determined that B was moving at 8.377 meters per second. And so this is going to be about 41.885. Oh, that's square, sorry. So that's going to be about 350.87. And that's going to be Newton meters. And of course, at maximum compression of the spring, or that T2, our velocity is 1/2 mass velocity 2 squared. But at maximum compression, this becomes 0. So that's going to be 0. So now we can use our equation. Use work energy T1, summation work from 1 to 2 equal T2. And T1 here was 350.87. Then the work up here was negative 1/2 times 1,000 times s squared. Over here, it's negative 29.43 s, and T2 is 0. Let me multiply that. It's going to be 500. Let me move it all to the left. So this is going to be an 500 s squared plus 29.43 s minus 350.87. And so it's going to be negative b plus or minus the square root of b squared minus 4 times a times c divided by 2a. And so using our quadratic formula, now when we use a quadratic formula, one answer is going to be negative, so that's not going to be relevant because we're compressing the spring, and one is positive, and that's going to be our answer 8087 meters. So that's going to be the maximum compression of the spring. So again, when we look at this problem, we had to do it in several steps because things were changing. We had the first step was to go from when A until it reached B, and then after the impact, and then after the compression of the spring. And we got the maximum compression to be 8087. Next, let's take a look at this problem. We have this truck colliding with a car, and the truck weighs 5 megagrams. That'd be 5,000 kilograms. The car is 2 megagrams or 2,000 kilograms. And after collision, the car moves with a velocity of 15 kilometers per hour to the right relative to the truck. Determine the coefficient of restitution and the loss of energy due to the collision. So let's take a look at this. So here the truck is moving 30,000 kilometers per hour, 30 kilometers per hour, 30,000 meters per hour. And if we divide that by 3,600, we get 8.33 meters per second. And this one divided by 3,600 gives us 2.78 meters per second. So after impact, velocity of B relative to A is 15 kilometers per hour, or again, 15,000 meters per hour. If you divide that by 3,600, we get, that's 3,600, Let me write that a little bit better. It's about 4.167 meters per second. Again, when it says relative, the B relative to A, that would imply that the velocity of B minus the velocity of A is 4.167 meters per second. Now, again, that would be just after impact, so we'll call that state 2. That's the relative velocity just after impact. And we can call this equation 1, probably going to refer to it. So the coefficient restitution now is E. Of course, that's going to be E is VB2 minus VBA over VA1 minus VB1. And so in the numerator, we have 4.167. Denominator, we have the velocity before impact, 8.33 minus 2.78. And we get coefficient of restitution of about 0.75. So now we want to find the energy loss. But first, we need to find velocities if we're going to calculate the energy loss. So for energy loss, we need velocities. And we can do conservation momentum. MA, VA1, MB, VB1 equals MA, VA2, MV, VB2. And if we so let's put everything in here. Let's put all our numbers in. We have 5,000 kilograms times 8.33. That's this here. Plus 2,000 kilograms times the velocity of the car, 2.78. Then after impact, we have 5,000 VA2 plus 2,000 VB2. So I just substituted the mass of the truck, the mass of the car on the left, mass of the truck, mass of the car on the right, and velocity before impact of the truck, velocity before impact of the car. And now let's substitute, let's maybe go up here. Let's say if we solve for VB2 and substitute it into here. So VB2 would be 4.176 plus VA2. So let's sub equation 1. And let's say on the left here, this all comes out to 47,210. And on the right, this is going to be, where's 5,000 VA2. Then if we substitute equation VB here into here, this is going to give us 2,000 VA2 plus 4.167. I substitute for VB2 there. And when we solve this, we get 47 to 10 equals, if we put these two together, it's going to be 7,000 VA2. And if we multiply these two out, we get 8334. Then finally, we solve this for VA2. Again, if we solve for VA2 here, we end up getting something like 5.55 meters per second. And if we substitute that back into equation 1, when the VB2, if we put it in here and bring V8 to the right, that's going to be that'll be negative here, but then positive here. That'll be 5. Six, 7. And we get VB2 of 972 meters per second. So we want to now find the change in energy. So energy before impact. Is 1/2 MA VA1 squared, 1/2 MB VB1 squared. So just the numbers before impact, of course, were 5,000 kilograms for the truck. And this velocity is 5.55 squared plus 1/2 2,000 kilograms for the car. And again, before impact, 2.78 meters per second. And if you put all this in your calculator, we get, oh, I think I made a mistake here. Please fix this. This was VA1. This should have been before impact. So this should have been 8.33. And this is all correct. And we'll put this in your calculator, 181, 2.7, and that's going to be Newton meters. And energy after impact. One half MA VA2 squared, 1/2 MB VB2 squared, 1/2 times 5,000. Again, this time now after the impact, this is 5.55. And this is 2,000. And again, the velocity 9.72. $171 or 85 Newton meters. So change in energy delta T is going to be from T1 minus T2 is 181 200.7 minus 141 485 ends up being 9716 Newton meters. So that would be the amount of energy lost during impact.